take a look at a slightly different signal, which is the non-causal signal. Let's call this example 3. Discrete time Fourier transform of this signal. Again, gamma of n, but u of negative n plus 1. And this is not causal because it's the signal has values when n is negative. Whereas in this case, this signal is causal because it's only defined when n is positive. For the non-causal case, let's plot it first. N xn. We need to know first when this is non-zero. This is mainly non-zero when this is not zero when negative n plus 1 is larger than or equal 0. So if we multiply by negative and then take this one to the other side, we get n is less than or equal -1. So this plot will be from n equals -1, and then it will start decaying and so on. Let's see. And the value of this one is gamma at -1, and so on. And here we are assuming that gamma is less than 1. The absolute value or the magnitude is less than 1. So it decay, and at the end, when we get a geometric series, it will converge. Now let's find the discrete time Fourier transform of this non-causal signal x exponential j omega is again a summation n from -infinity to +infinity xn exponential minus j omega n, which is from -infinity to +infinity, and xn in this case is gamma n gamma n u minus n plus 1 exponential minus j omega n. And as we have seen here, that this is non-zero only when n is less than -1. So the limits of the summation will be now from -infinity till -1. So because we are only non-zero when n is less than or equal -1. So -infinity to -1 gamma n, and over this range, this u minus n plus 1 will be 1. And what's left is minus exponential minus j omega n. And again, we'll do similar things. We'll combine those two terms. N equals -infinity to -1. We combine those two, gamma exponential minus j omega whole to the power n. Okay. We can change the variable of the summation to make it similar to to make it similar to what we had before, similar to this geometric series, and we'll be able to evaluate it by, let's say, n, we'll define a new variable equals minus n. So the summation limits will be flipped. We'll have m from 1 to infinity, to plus infinity, and then gamma exponential minus j omega to the power minus m, because n equals minus m, or vice versa. So this will be written as m equals 1 to infinity, and then we can write it this way, exponential j omega divided by gamma to the power m. If we just if we write this as gamma exponential minus j omega power minus 1 and then to the power m. So, or if we just like do 1 divided by this to the power m, we will have this term. And now for this one to converge, this one should be less than 1. Oh, sorry. I think I have, yeah, I have made a mistake. Yeah. For this non-causal, because here this will not converge if if the absolute value of gamma is less than 1, this might not converge because the overall will be larger than 1. So the mistake that I have made here is that for the non-causal signal, the absolute value of gamma should be larger than 1. Larger than 1. And here, because the power is negative, it's decaying. Okay. Now, for this one to converge, by the way, we can make it also from m equals 0 to infinity if we want. So we're starting from 0. So if we subtract one term from this, m equals 0. When m equals 0, we have it will be 1. So this thing, it will be as if a summation from m equals 0 to plus infinity exponential j omega divided by gamma power m minus, so this thing minus the term when m equals 0, because we have added it here, so we subtracted here, minus 1, because when m equals 0, this would be 1, so minus 1. Now we have this geometric series similar to what we have before, and the condition for this to converge is similarly, this thing should be the magnitude of this thing should be less than 1, so magnitude of exponential j omega divided by gamma should be less than 1, which is 1 divided by gamma should be less than 1, and therefore the magnitude or the absolute value of gamma should be larger than 1, which is satisfied because we assume this from the beginning. The absolute value of gamma should be larger than 1 for this non-causal signal, for it to converge, or for it to have a discrete time Fourier transform. and then it converges. And it converges to this value, 1 divided by 1 minus this. So exponential j omega divided by gamma. And then we have minus 1 here. Can rewrite it as 1 minus 1 plus exponential j omega divided by gamma divided by 1 minus exponential j omega divided by gamma. And then those will cancel. So we'll have exponential j omega divided by, we multiply by this gamma here, gamma minus exponential j omega. We can also, to write it in a similar form, similar to this form, we can multiply by exponential minus j omega. We multiply by, right here, times exponential minus j omega divided by exponential minus j omega. And this will be 1 divided by gamma exponential minus j omega minus 1. This x j omega. And this is the discrete Fourier transform of gamma n u minus n plus 1. And when the magnitude of gamma is larger than 1. Those are very, very, very useful. And especially this one, the causal